Go ahead.
Go ahead?
Yeah.
All right. Well, thank you very much for coming here on the last day before Thanksgiving break. So what I'm here to do is introduce you to a couple of different things. First of all, computational science and engineering. What is it? Where can you use it? How do you get started? And there's going to be three of us who will speak, so I'll talk for about 15 minutes, and then Eric Jankowski from Material Science will talk about what he does, and Min Long from Computer Science will talk about what he does. So hopefully that will give you a broad overview of what computational science is. I want to thank Justin for having organized this event. He did a great job on the promotional material. Okay, well, what is it? Well, so the idea, how many of you have heard of computational science as opposed to computer science? So not pretty good. So so some you have a clue, right? It's very clearly not computer science. It of course uses computer science ideas, but we tend to think of computational science as being much more related to the idea of solving equations for using in investigating questions of scientific or engineering interest. Okay, so the idea is so we think of it as mathematics plus computer science applied to scientific or engineering disciplines. Okay, and so the traditional way to make progress in, say, science or engineering is to do laboratory experimentation or sort of theoretical pencil and paper work. But at least I would say for the last probably 30, 40 years, computational science has been a major investigative tool in making progress in these areas. Okay? So we use computer models to investigate these questions. So the question you might have is, where do these models come from? What kinds of things are we modeling? Who builds them? How do these things come into existence? And how do I get started? Suppose you like all of this. What do you do to get into this field? Okay. So I'm going to use an example from fluid dynamics. I think most of you engineering students have to take at some point a fluids course, right? So these equations shouldn't be too unfamiliar. What I have here is an example. Now this is sort of an example. This is a classic use of computational science. The idea is that we want to solve these equations. So scientists and engineers will develop model equations, and for us, the model might look like this. We have a velocity field, a pressure field, some kind of viscous term, and then we have a constraint on the velocity that says that the flow, for this particular example, should be incompressible. We shouldn't be able to compress it. It's not a gas that we can compress into a box, let's say. Okay, so now, at least in all but the simplest cases, we're not going to be able to solve these equations. Okay, so we could write down really simple one-dimensional versions of this equation that you might be able to solve. But as soon as you go into 2 dimensions and 3 dimensions, we're going to need to do something computationally. Okay, again, except for in the very simplest of cases. So what does that mean to solve these equations computationally? Well, it means we have to discretize them, usually, and there's various ways of doing it. But often, when we discretize these equations, and this is where a mathematician comes in, the mathematician looks at those model equations that a scientist or an engineer has come up with and says, well, gee, can we solve these equations? And often the first thing you have to do as a mathematician is look and see if there even is a solution to these equations. Okay, if we write down the system of equations, there's no guarantee that there is even a solution. But for Navier-Stokes, that's pretty well established that there are solutions, okay? Although even there's sort of questions that remain unanswered in the mathematical world. All right, so a computational mathematician has to design numerical methods for solving these equations accurately on a computer. And if you've had a computational methods course, like in the math department, we offer Scientific Computing 365. We offer a numerical methods course, 465. And then we offer, in fact, a series of 3 semesters of numerical methods. So that's how much it really takes to cover everything you might need to, say, solve this system of equations accurately. Okay? Well, one of the things that comes out of this, now I'm only showing you a piece of what you have to do if you want to solve these equations. one thing that comes out is a big linear system of equations that look like this. Now most of you, again, have solved little 2x2 systems. Maybe you've solved a 3x3 system by hand. And if you've had a MATLAB course, or you've probably seen that even with, with MATLAB, which is a fairly easy to use scientific computing language, we can actually solve really large systems of equations. When I teach 365, I have students solve systems that are on the order of 100,000 unknowns. Okay, so that of course is assuming that we have lots of zeros. Otherwise there would be no hope of being able to do it. But if we have enough zeros in this system, we can actually solve these equations, okay? And so typically, and this is the pressure here, so this is often the pressure is a constraint that is satisfied by a linear system that looks like this. So we have, for a large 3D system of equations, you want to do fluid flow over a car, for example, you could end up with millions of unknowns. And in fact, a lot of the large software packages that do things like model flow over automobiles or airplanes, the key component in their package is methods for solving this type of equation. So how do we solve these large systems fast? Okay, we don't want to spend all day solving this system or we'll never get any kind of solution. So this is where the computer scientist comes in. So computer scientists work with mathematicians to use latest hardware advances and architecture to solve these large systems. So of course at some point we have to start with a processor. And now modern processors are extremely complicated. Okay, it's no longer just a matter of let's count the number of operations in our solve. Those of you who've taken, again, like in 365, Math 365, the scientific computing course, we look at that linear system solve and we count the number of operations in, say, a Gaussian elimination, the thing that you learn to do by hand. How many of you remember the order of operations in Gaussian elimination? Right? Oh, okay. How many? 2/3 n cubed. Perfect. Brady, you did a good job.
That's correct.
My students could remember that from 1 week to the next. I'd be right back. Yes, exactly. So if we have a matrix with n by n entries, it's going to take order n cubed operations. And of course, that's one way to measure the operation count. But more recently, the bigger issue is we've got several cores here. I want to be able to distribute those operations over 4 cores. I want to be able to, I have to worry about memory hierarchies. Sometimes it becomes a challenge if we put things in memory, and then we have to be able to pull them out of memory quickly. Okay, so a lot of those things are now becoming as expensive as simply counting the number of operations. So computer scientists have to work with mathematicians are going to have to work with computer scientists to design algorithms which solve this system accurately and which do it in a way that makes maximum use of this complicated hardware. More recently, people are doing things on GPUs. This has become a really popular method for accelerating systems. And of course, what we ultimately want to do is go to supercomputers. So here's the supercomputer in Texas, Stampede. And here's the one in Argonne, Mira. The US has several large supercomputers. I can't remember. These have on the order of 500,000 to 1 million cores each. If you're really interested in the state of art of supercomputers, you should go check out top500.org. Yesterday, I think actually today, they just came out with their new list. They come out with a list of the top 500 computers in the world, and they just came out with a new list yesterday. China is, I think, the top 5. Okay, US comes at number 6 or number 7. So, and what of course, everybody's working towards is an exascale machine. Most of your laptops are gigaflops, that will say 10 to 100 gigaflops. That's 10 to the 9th flops. The next one is petaflop, a teraflop. Petaflop, these are all basically in the petaflop range, and then what we're all going for is an exascale machine. Okay? And so that's where the hard work is really going to start, is working with computer science and mathematicians to really see if we can actually run on machines that have on the order of 1 million cores. Okay, not just 4 cores like your desktop, but 1 million. All right. Okay, then finally, somehow software engineers, and once we write these fabulous, we design these algorithms that can work on computers, software engineers have to have software that's actually usable. The community needs to be able to use this. So actually, ultimately, a lot of the details of how these systems get solved needs to be hidden from the user for the most part. If you're somebody who wants to actually solve a computational science problem, you have a real fluids problem that you want to solve. You don't want to have to worry about, the details of how that algorithm gets implemented on a supercomputer. You hope that somebody with software expertise has done that for you. And this is just a very minor listing of the types of software. These are all open source packages that people have put lots of effort into designing so that they're easy to use. LAPACK, how many of you have heard of LAPACK? That's okay, not too many. Okay, good. So this is actually when you solve AX equals B in MATLAB. A/B, it's behind the scenes, it's using a LAPACK algorithm. So this is code, it's a Fortran or C code you can download. Phoenix is a finite element project, an open source finite element project. PETC is a set of solver libraries. These are all open source. DEAL2, we had a speaker last week in our computing seminar who told us all about DEAL2. He's a designer of DEAL2. Recently won a Wilkinson Prize in software engineering. Fishpack, mostly I picked this one because I like the logo. It's actually a fairly old code, but it solves that Poisson problem. For the pressure, for example, using really fast methods. So this is probably about the fastest method. It has limitations, though, in that it can't really work on anything other than a square. Trilinos is a big package that comes out of Livermore. So there's lots of these packages. So there's lots of work for software engineers who like the idea of taking complicated algorithms and presenting them to users, okay, in a way that's easy to use. So finally, how can you get started in this? Well, we have a CSE Minor. How many of you know about the minor in computational science? Okay, so most of you have, at least some of you, half of you have heard of it. That's good. It's been started a couple of years ago. There's actually a web page for the CSE Minor. I'll click on that in a minute. We have a new PhD programming with it. BSU has a new computing PhD with an emphasis in computational science and engineering. Career-wise, there's lots of places where people use these skills. National laboratories are huge consumers of people with expertise in computational science. Commercial software companies, MathWorks, CD at APCO in Seattle does finite element analysis. Universities, of course, we all use these tools if we're doing I would say a lot of researchers are heavily involved in computational work. Manufacturing companies, of course, are also doing, I should have added an automobile company, they're all doing computational fluid dynamics and running these big software packages. I think at this point I'm just going to say a few things about what I do. So I come at this world as a mathematician, and I develop a software package that is similar to the other ones. Okay, I have a project called Forest Claw, which I work on, which is a highly scalable, so it runs on a large number of processors, and it does what's called adaptive mesh refinement. I'll just show you a picture here. So the idea is that we're not going to solve on just one mesh. We want to adaptively refine where we want high resolution and not so much where we have low resolution. Okay. So the idea is that we have several grids. Each one of these little squares is a grid. And we can and this is the sort of thing that we can do. This is a really simple problem, just a scalar advection in a swirling flow. Okay, so managing this, making sure all these boxes can communicate with each other and doing it in a parallel environment raises all kinds of challenges. And of course, we want to run this on multiple processors. So we imagine taking our domain, all these different colors refer to our different process jobs. So we put it on, say, different cores on a laptop or different processors. Okay. And finally, I guess this is one project I've been involved in most recently, is using this code to do simulation of an ash plume in the atmosphere. So the USGS is very interesting in monitoring where, in the event of a volcanic eruption, it's very interested in modeling where does the ash go. Okay, so we've taken a code, and we've taken an existing code that they had and put it into our adaptive mesh refinement code. And so now we can make it, or now their code runs in parallel with adaptive mesh refinement. Okay? And I think I'm going to stop there. And I'm going to let, which one of you is going to go next? Eric's going to go next. Okay, and I think at the end what we're going to do is have questions. So we'll have a bit of a panel discussion. So if you have questions, you can ask any one of us at the end. Okay?
Hi, I'm Eric. I'm in Material Science and Engineering, and I'm another computational scientist. I think about, so I come from an engineering background where I avoided computation as long as I could. I thought like I wasn't a computer person. This is not my thing. I'm just gonna play with chemicals, which I know about, and I'll get a job at a manufacturing company doing that sort of stuff. But towards the end of my undergraduate career, I did some research with a professor who's doing some computational chemical engineering. And when I started using software, using computer algorithms to solve problems in engineering that I couldn't solve by pencil and paper otherwise, I was like, ooh, actually, this is pretty neat. I'm gonna keep doing this sort of stuff. And so this animation is an example of the output from one of the simulations that my lab does now. So my lab does, we do molecular dynamics and Monte Carlo simulations where we try to look at how the shapes and interactions between molecules influence how they pack. And so this is a model of a system where what I've done is just well, let's see if I can get this to rotate correctly. Here we're modeling a bunch of copies of the same kind of molecule that are used inside organic solar cells. And in this particular simulation, we found some conditions where if we visualize the system so that it doesn't have those blue floppy side chains, we can see that it forms stacks. There's some ordering in those stacks. You can see that there's a bunch of layers of these molecules in this particular system. And so we use computer simulations to solve problems that relate property or interactions with structure for materials problems. And these pop up in tons of other domains. So there's a really cool research program out of Stanford called Eterna, where you can play this game, and by playing this game, you are proposing, if you get good at the game, you're proposing experiments that actually get run in a lab where someone synthesizes this RNA. Actually, now it's a robot that synthesizes the RNA. That RNA gets synthesized and is put into a situation where they see if it binds with other proteins or drugs to see if it'll make an effective medicine. So you can like change around the different bases on here, and if you get it right, then you get bubbles and lights and stuff. And so computational scientists are the people that bridge the domain science that's important in getting the physics right and the actual implementation of the computational code that makes programs like this go. So I kind of think about software as it overlaps with engineering in kind of three levels. There's computational literacy, which is getting our feet wet with things like MATLAB and like knowing a little bit about how our operating systems work so that we can like just like turn on Excel and like get a couple of like things done for like our homework. That's like computational literacy. Then above that is computational science. That's the thing that we target with the minor. This is getting our hands wet with the nitty-gritty details of matrix multiplication and how that parallelizes onto complicated architectures. And then once you've got a background in computational science and engineering, that opens doors to high-performance computing. It's what lets us go to those supercomputers and run the simulations like I was showing here, so that we can start having answers for meaningful engineering problems that demand that kind of computation. And so students from my lab and labs like mine go to work at companies like Schrodinger that build software for modeling molecules like this, or that go to the Foldit team. This is another game that you can play to contribute to science. This is a protein that you can move around, and if you grab the ligands and move them away in the right way, you also get a bunch of flashing lights, I think, except for clearly I have not done this one right. So other students that work in these kinds of areas go to places like Airbnb. What is the best way, and this is a job that pays really, really well, what is the best way to turn a stolen credit card number into money for you? Like if you steal your friend's or now your enemy's credit card, how do you turn that into cash? I mean, like you can buy like a thing, but then the credit card gets declined after that fraudulent charge shows up. So like you get like one thing, and then the credit card number doesn't work anymore.
Buy
But
gift cards?
what?
Gift cards?
Gift cards, you can buy a couple, but like it's hard to turn that credit card into cash if you've stolen it. But if you put your room up for rent on Airbnb and then rent it from yourself, you can turn that credit card into some amount of cash that you can actually use for anything. So I have a friend that works at Airbnb now with a background in molecular sciences, where the math and the computations that we do are, we're trying to extract information from large collections of data. In this single snapshot, we've got a few thousand atoms, and we need to know something about their aggregate positions that tells us the properties of this material. We've got thousands and thousands of these snapshots that we're trying to extract information about. So he's applying these tools at Airbnb. Every day there's thousands and thousands of transactions that occur, and he looks for anomalies in these transactions to try to figure out who has stolen credit cards so that they can make sure that those credit cards are flagged and not turned into cash in an illegal way. Other friends are working at Boeing doing exactly this modeling, so trying to figure out how the properties of epoxies depend upon how we process them, so doing molecular modeling at companies. I think it's, for those of you that are interested in the computational science track, developing skills beyond the computational literacy skills, I think puts you at the forefront of participating in the digital economy that's everywhere now. If you don't understand the code that is making your phones work, your cars work, your computers work, you're kind of you have to just kind of like go where the tides take you. But if you understand what's going on under the hood, you get to control that and profit from that. So if you want that power in tomorrow's world, getting involved in computational science and engineering, I think is a good investment. So I'm going to pause there and let Min talk, and then we'll open it up for questions at the end.
How to guess the green point?
It's that top, just under the
Top
little
one, okay, I
screen.
see that, yeah. Oh, it works.
Yeah.
Okay. So, hello everyone. My name is Ming Long. I'm an assistant professor from the computer science department. And my background is computational physics. So today, Donna asked me to talk something about the careers in computational science and engineering. And more specifically, what's going on?
One of the buttons makes it turn black, so push the last one and push it again.
Okay. It's embarrassing.
Like having computational scientists to run the pointer.
Yeah, we do need support. So which one is turning on? Oh, this one turn again, okay. I should try before the talk, yeah. Okay. Works.
As a computational scientist, you'll learn that all of the software that exists in the world is cobbled together by bits of twine and like duct tape. Everything
That's
is broken
two.
and everything is terrible.
Okay, let's just use mine. I prefer for my
Except for our own
so I
personal
have-
code. That's perfect.
Mechanical engineers appreciate duct tape.
Yeah, this works. So So first, I will talk about how computational science can benefit our research. I will give you two examples which I'm carrying out right now. One is from the nuclear material science, one is from the astrophysics. And secondly, we will talk about computational science, what it is and why it's important. And lastly, Donna asked me to address the needs of the computer science in the computational science. So that's the outline for today's presentation. So first example is from the computational nuclear materials. And as we know, this is a grain boundary evolution modeling in the nuclear fuels. These nuclear fuels including the uranium oxide, dioxide, and uranium silicide. As we know, U-235 is not a stable isotope. It can decay into smaller pieces and release gas. This gas will diffuse. And this gas can also cause the formation of the bubbles. And furtherly, they will affect the thermal and mechanical properties of the nuclear fuels. So this is a background. And however, it turns out the evolution of the grains of these smaller pieces plays a very important role to determine the thermal conductivity, to change the fuel performance or something like that. So it's a key issue in the fuel performance study. However, this kind of work cannot be well studied through the experimental testing because it's too small and changing too fast and some other reasons. So instead, a technique called phase field simulation is a very useful tool to simulate these cases. Here is an example. We use the Moore's framework, which is FEM method package to solve the PD equations to mimic the growth, to mimic the evolution of these grains. And here we can see the grain size change drastically and will affect the overall thermal conductivity will decrease and affect our fuel performance. So this is one example. We are not doing something imaginary. We are doing something with really solid foundation. This phase field method has been well tested by some other cases. For example, this is grain boundary evolution. This is crystal evolution, snow crystal evolution. This has been validated. So we are really doing something great. Yeah, not mimic. Yeah. So here is the second case which I'm doing. As we know, the center of the galaxy is a black hole, hosted by a black hole. It's a supermassive black hole. And the black hole will accrete anything they can absorb nearby. And this matter will flow to the black hole, and part of them will be ejected by releasing a huge amount of energy. So it's pretty much like the heartbeat of the galaxy. So the observational community tried very hard to get the direct image around the black hole. And you can see they tried very hard but cannot resolve it clearly. So the question is, how can we solve this problem if we do not know the details nearby the galaxy, nearby the black hole? So observation might be helpful but not extremely useful. So instead, we are using simulation, using modeling to do the work. This is the simulation, actually, test simulation of a curved black hole, which I did this week. And the center is a black hole, and this is a toric, represents the accretion materials surrounding the black hole. And the materials will go to the black hole, and part of them, again, ejected and release huge amount of energy. So this is another example how we can use computational science in our research. The key point is experiment or observation might be not very useful in these cases, and we really need some creative method to study that. So these are two examples. So next, I will just briefly explain what's computational science, because Donna has explained that very well. So my conclusion is, computational science or engineering is, we focus on problems in science and engineering, not politics, not community problems, society problems, only science and engineering. We want a numeric method, numeric analysis, not scratch paper and pencil. So we want to use really develop the numeric methods. And also, we want a computational implementation. So what does it mean? It means method, for example, Lagrange interpolation, for example, Riemann solver is over there. However, how can you translate them into the languages that computers, the supercomputers can understand is another issue. We call this is computational implementation. It's a really important issue. Lastly is the computer techniques. How we build the fast supercomputers, how we build faster clusters, GPUs, whatever. This is called computer science techniques. All of them together will be defined as computational science and engineering. So in my class, some of you may be my student in the mechanical engineering 271 or CS 507. So I give my short answer for computational science. It's a multidisciplinary study of solving complex problems in science and engineering in numerical and computational way. So that's basically about the computational science. So next, why we want to use computational science? By using the two examples that I showed you just now, we can see the motivations. First, most of the problems are non-linear, means it's not easy to solve. Secondly,
Linear problems are hard.
linear is hard too, yeah. And most linear problems cannot be solved by the scratch paper, as I said. We have to rely on some techniques to do that job. Thirdly, numerical methods developed really quick, really fast, and also computing power grows really fast during the last decade. So when I was a student, I cannot use my slow computer to solve such kind of simulations. But nowadays, with powerful CPUs, with powerful supercomputers, it's really doable. So that's a reason. And it turns out a lot of achievements has been made in the past decades. For example, computational physics, computational engineering, computational biology, maybe computational material science either. So we can conclude that computational science is more important nowadays because of these reasons. So there is a new idea, or not very new idea, about the role of the computational science in the human history. So here it is. We think that computational science is the third pillar in the scientific discovery. So as we know, human beings learned the rules of the universe first from our experience or experiments. Secondly, we abstract the underlying mechanisms and get the theory. So that's an experiment, theory. That's the two pillars. And recently, because of the growth of the numerical methods, because of the growth of the computing powers, we can really do computation to discover new things we never know before. So that's a role of the computational science in research. The composition, so it's not very sensitive. The composition of the computational science is composed by three components. The first one is math. So we really need to use math method to solve the discrete our equations, to solve the equations. Secondly, we want to solve science problems. So we really need some background in the material science, in physics, in engineering. Otherwise, you don't know what kind of problems you are going to solve, right? So thirdly, computer science plays a more important role nowadays. I will show you later. So if you are a computational scientist, your position is really unique. You are middle of the heart here. Yeah. Okay. So recently, to address the needs of the growth of the computational science, Boise State University established a new computing PhD program in 2016. And that's the description of the motivation of this program. And you see, we solve the problems in science and engineering by using numeric methods, by using computational methods. So the university realized the issue, the needs of the computational science. And this is a course plan for the PhD program. And I categorize them as three groups. First is math, numeric method 1, 2, 3. Statistics actually, and some basic math, and also some courses from the computer science. The first one is what I'm teaching, computing foundation for the computational science, and another one is parallel computing. And also, students are required to have some background in science or engineering. Otherwise, you just have tools, but you don't know what targets you want to deal with. So next, it might be very easy to understand we need maths, we need science, but why we need computer science? That's a question. So before I answer this question, why computer science? Let's go through these questions. It's from a very famous professor in Princeton, computer science professor in Princeton. Have you ever wasted a lot of time coding the wrong algorithms? Might be, right? Very frustrated sometimes, right? So have you used a data structure that's too much complicated to be implemented to solve your problem? Have you tested a program but missed an obvious problem? God, I can catch this problem in a few seconds, but why I wasted so many days? Got stuck. Have you spent a day looking for a bug, but you should be able to find it in 5 minutes? Have you needed to make a program run 3 times faster? Yeah, you can run some code, but it's not faster. You need to spend 1 year to get your result. Not very acceptable. Have you struggled to move a program from workstation to a computer? So this is called scaling, something like that. You can write from a computer nicely, but you cannot write from the supercomputer. So that's a problem. Have you tried to make modest change in someone else's program? Horrible, right? If there's no documentation. Have you rewritten program because you couldn't understand it? It's totally useless. Why not? I just forget this one. Just write the code from the scratch. That's one solution, but not the best solution. So was it fun? So there's a place that computer science will take into the steps. Yeah. Really not sensitive. Okay, next, let's take a look at a survey in a very prestigious university. The question is like that. What do you know well? The question is about the programming. The question is about the basic computer science. Okay, we have 51 replies from the 14 departments, so it's really a multidisciplinary course. So MATLAB, okay, 60%. I believe everyone here understands MATLAB, right? Okay. Python, 11. C++, Fortran. Fortran is horrible, right? Matplotlib, R, and it's useful for some, you know that, commercial stuff. SVN, version control, NPI, Make, GDB. They are just the fundamental things for the program. You see, even in this university, I won't tell you the name, but you see. Yeah. So we really need some training in the computer science, especially in the programming side. So I did some survey in my class. Write a hello world C++ code without any reference. Well, result. Maybe Taylor can tell everyone what happened, right? Yeah, not very good. So all these surveys do not touch some advanced topics, just some basic programming. But you can see the background from the science majors, from the engineering majors, it's not that solid in the computer science. So additional topics, advanced topics like the object-oriented design, data structure algorithms, high-performance computing, complexity, all these things, we haven't do this survey. And they are very useful actually. So I will give you an example how useful these advanced things would be. So in short, we can answer the question why computer science is important, because computer science can provide us techniques, tools, and principles of writing some high quality code. You can write code, but you may not be able to write correct code or even high quality code. So that's the role of the computer science in computational science. And here is a research example, and from the phase field simulation I did in the first slide. And we know, okay, the RPD is very complex, but we don't care at this moment. So a system of coupled PDEs, the PDEs will describe one model of the materials, And this model will be solved by using the MOOS framework developed by the Idaho National Lab, right? So the question is, now we have one model. How can we build a new model? We change the materials from the uranium dioxide to the uranium silicide. We change the temperature. We change the size of the fuel pellet or something like that. So how can we build a new model? Actually, it involves a lot of changes in the source terms in these equations. So can we simply building a model by changing the parameters? The answers might not be like that because the problem will be more complex. Can we rewrite the code significantly? Okay, I don't know how to implement this stuff, so let's just write a new model. That's a solution, but it's a waste of the time. So the solution might be very simple. So if you know the inheritance from the C++ programming course, you will know that. Okay, why not use our object-oriented architecture to construct your code? And then each term in the equations can be separated and created as a base class. Base class represents some basic data structure and methods over there. And then when you need to implement a new model, you can just construct some derived class, which will inherit from the base class. So we will have some new features, but we will also keep the old features we want. This is called inheritance. And by doing so, your job will be easier. So life could be much easier. Now we create a new model, just use the inheritance and extend the base classes to the derived classes, and then provide the changed things in the right-hand side of the equation, which represents your new materials or something like that. Then you can do a new model based on your old model. So that would be very useful. So you don't need to spend weeks, months to rewrite your code, and simply make use of the existing code. So this is another example. And at the end, we can summarize. So I hope my talk is not that horrible, so everyone can understand why computational science is important, why computer science is important, right? So I didn't list my answers here, but I think everyone can kind of know that. Secondly, I want to talk about the career plans. So you can do a much better job and become very popular in the job market if you are trained computational scientist. The reason, first, you know something much better than scientists and engineers because they don't know computer science. Second, you know something much better than computer science because they do not know science or engineering. So this will make you be in a unique position and will be very popular. And the third reason is you can easily extend your research or extend your career to be a data scientist, which is one of the most popular positions nowadays. So that's the third reason. In addition, as far as I know, there is a huge need for the trained computational scientists or data scientists nowadays. And if you have, actually there are more reasons to be a computational scientist. So take my class, you will know more answers, and join my group, you will know more answers. So thank you. Yeah.
Okay, so
You can leave the discussion.
yeah, so I guess what I thought I would do, and I realized I didn't, was show the yeah. So why don't we I'll show the minor program so you actually see the page. Let's see, I guess I have it here. Yeah, and if, in case you had any specific questions about the minor degree, you can ask about that. Are there any questions, by the way? Go ahead and let me get my act together here. Okay, here we go. Let's see, it might be helpful if I have this on the screen. Okay, so here was the, so if you go to the ME department and you click on undergraduates, down here you'll see, or this is the, yeah, is that up there? Okay. So you'll see down here, there's the Computational Science and Engineering Minor. Okay, so we click here. And I'm actually the coordinator. This is a new thing, so I don't know all the answers to everything yet. But we have, so here's the program. And here are the sort of contact people in different departments. Tim Anderson, although I'm kind of thinking we should include Min and try to add more contacts. So I'm sure Min would be more than happy to answer any questions. Eric in engineering, and then myself, Grady, who's sitting here in the front, Professor Wright, and Jody Mead, who's actually been very involved in developing our PhD program in computing. And here's the schedule of courses that are needed. So you've got to take 2 courses, either this set of courses or this set of courses. I understand there was recently a change to 253. Is that right? It has a new requirement or something? So Min could answer any questions about computer science degrees. You have to take several math courses, so Calculus 2, differential equations, and then one of the numerics courses that we offer. And then finally, a parallel computing course. So there's two courses that are offered. One is offered through the CS department. Second one is offered through ME. I'll be teaching the ME program, parallel computing course in the spring. And then one upper division course with a computational emphasis, and there's going to be a wide variety of courses that will satisfy that requirement. So if any of you are interested in thinking about this minor, you may already have collected a lot of these courses in the course of doing your undergraduate degree, and if you add a few more, you might well end up with a CSE minor. Questions about?
Yeah. I noticed, I saw, I think I was looking at a different page, but very similar, that you can replace one of the upper level electives with an internship, and that has to be approved actually through you. I was just curious what kind of internships you feel would satisfy the computational minor.
So it would have to involve some computing.
Yeah.
So here would be an ideal example. So Idaho National Labs has a summer internship program that you would most likely be involved doing some kind of computing. That would certainly qualify. I would imagine that the type of internships you might get at, say, Clearwater, even though that's a financial company, if there was a significant computing component, that would work.
Yeah, the first place I would look is National Labs. I know it. I don't know about Micron, but I should. But like the National Renewable Energy Lab and NIST, they've got SULI internships that are targeted at undergraduates. And I know a couple of our undergraduates that went to NIST last summer were doing scientific computing there.
Yes?
One of the things that I've noticed with the ME program is that a large amount of what you're asking for in the minor can already be built into an ME degree. Why would someone want to actually add the minor on?
I think because I would think that an employer would look at that and see that this is a desire, that you've actually, that you know what computational science is. If you've signed up for the degree, there's a chance that you kind of know what it means, and which is a good thing. And then I would think that it just shows that you actually have some additional skills beyond which is typically required by an ME degree. I think.
I'm not super familiar with the ME curriculum, but I'll flip that on its head. If there's a lot of overlap with the ME curriculum in these courses, then if it's a matter of taking 2 or 3 more classes to get the minor, then why not? If you're already trained in that way.
I taught ME class this spring. It's ME 271. As far as I know, most of the students is lack of programming experience in C++, which is kind of important if you want to do computational science in future. So it's worth to add some, take some courses and to be a minor, something like that. Yeah.
I might push back on that just a little bit. I do a lot of sort of high-end performing computing, and I use a lot of these legacy codes are written in Fortran, And so you may be hearing things like Fortran is a horrible language. It's absolutely not. It turns out to be a really efficient and easy way to do a lot of I view it very much as a low-level language that should definitely be combined with something like C++. If you need to do large data structure management, so you want to be doing that in C or C++. But under the hood, a lot of codes are written in Fortran. And so you should not be shy away from any code written in Fortran just because you think Fortran was a code that was developed in the 60s and died somewhere in 1975. If you go online, you'll find a huge number of codes are still written in Fortran. Okay.
Yeah,
So,
if you think people have strong opinions about religions, just wait until you
try
get
different languages.
these,
And in C++, as the benefits of it are enormous, but it's also easy to get carried away and spend more of your time trying to figure out which is the perfect base class to inherit from all of your, C++, what I always heard is hindsight, hindsight is 20/20, meaning once you've developed everything, now you know what the perfect base class is, and then you go back and you rewrite your base class so that you can now inherit all this beautiful structure. Or, in my opinion, C++ or scientific computing is often just procedural. You have procedures and algorithms, and you can get a little carried away with the objects, just to introduce a little controversy. But it's true that a lot of the modern software packages are written in C++.
Yeah, you don't need to persuade me because my first language is Fortran.
Yeah.
I always use Fortran when I was in Chicago,
Yeah.
University of Chicago. Yeah.
Yeah. And it can make these codes really hard to read sometimes. Oh, anyway. How many of you feel like you're good at C++?
He's my student.
Yeah, okay, good. All right. MATLAB? Python? Any Python users? Okay, 1, 2, okay, which do you like better, Python or MATLAB?
Python.
Yeah, why?
It's free. You can download it anywhere.
Yeah, exactly.
By the way, he's also my student.
Any Fortran users? Oh, okay, good, all right.
There's a little bit of a concern, particularly with my situation. I'm a mechanical engineer major, and I don't have much coding experience. I have taken C++ over the summer. That's pretty much it. A few assignments in MATLAB. But I understand this is something that could make me distinct in the field, and also could spark some kind of interest. Obviously, it's going to help me a whole lot in trying to find a job. But I already have an internship, and there's a pretty high demand in the curriculum already. So going after a minor, I do have a concern of the workload and the effect it might have on my GPA. And so I don't know if you can alleviate some of that concern or confirm it, but I'm just curious. Probably worth it.
The minor is one path that may make sense for some students for getting some additional computational science and engineering training. But there are other things on campus that can help buttress your degrees. The university just got institutional membership with Software Carpentry. So this is an organization whose focus is helping scientists use code to get research done faster. And so we'll be having software carpentry workshops throughout the year. These are 1 or 2 day workshops where you can come in and gain some of these computational skills. And they're focused on things like Bash, Git, and Python, so that you can take the skills you learn in those workshops and start applying them into your research programs basically that day. And that's not a class that takes very much away from the already large demands on our schedules, trying to finish up an engineering program. But maybe I should be doing a better job as an advisor for the CSE program to sell it. But right, if I would recommend, if it's something that you think that you're interested in, finding workshops like the software carpentry workshops, or doing a semester of research in someone's lab on campus to get your feet wet, to see if there's that spark there where you're like, oh yeah, this is something that I want to dive into, 16 credits of, or if it doesn't make sense, if it doesn't shout to you like, I need to do this, don't don't let us twist your arm.
Oh, but I might add, so Min's slide about all the things, did you spend a whole day debugging a code? Did you that you could have found, once you found the bug, it took you 5 minutes? I mean, we've all had that experience, right? And at the very last line though, was it fun? I don't know if you emphasize this, but the point is that if you're somebody, yes, you may feel like you just spent a whole day trying to debug a code, but did you have fun? And if you're somebody that can say yes, then you should not you should not be discouraged by the fact that it took you that whole day to find that bug, because everybody has that experience. The most senior experienced computational scientists will tell you how many days they feel like they, quote, wasted looking for bugs that were easy to find in the end. Okay, and you get slightly better at it, and but it is part of the game. And so and it is true that these courses are harder. They can be harder than, because there's a real technical skill at the bottom that you have to have, and either your code runs or it doesn't. There's no partial credit in computational science, right? If we're in a good mood, we'll look at your code and say, yeah, you had the right idea, but you forgot to do X, But if we're not in a good mood, we're going to say you didn't get the right answer, and I'm sorry, but this isn't going to fly, And so we can be, it's like a proof almost, without partial credit. So it's hard. And so people who do really well in other math courses, for example, can often have a hard time in our computational courses because we don't do a good enough job of getting people using computational tools early on. They should be using it in their freshman and sophomore years, and the first time people often see some of these courses is maybe a junior, maybe a senior year. So they struggle with the programming. The math often isn't the problem. And so I don't know what to say. I mean, it is true that these courses typically can be harder, but that shouldn't discourage anybody from taking them, because the skills you learn are really valuable.
I'll flip that on its head a little bit. I think that that phrasing sounds scary and would discourage students.
Oh, sorry.
As instructors of computational science, if we haven't provided the scaffolding from where our students begin to the skills that we want them to have, we haven't done our job.
Well, yeah, we haven't in a lot of ways.
And so yeah, it's I think that I've got a pretty young lab here, so our sample size is small, but we've got 12 students that we've taken from no programming experience to doing this research that we do. They're now funded by Idaho National Lab and Boeing and some other companies, and so it is something that is totally doable. It sounds scary, and it can sound scarier depending upon who you talk to. But it's as accessible as everything else. You just need to find the right lens for figuring out how to make yourself excited about it.
I was actually going to let Grady weigh in here. So Professor Wright also teaches our numerics courses, and he may have comments on this. Or not. Don't mean to put you on the spot.
You guys are covering pretty good, so. Yeah, but I was going to ask about this, I think as Min asked about this connection with data science and computational science, because you hear these terms, data science is the latest, greatest thing, but a lot of data science is computational science, so it'd be nice if we made that connection maybe a little bit better.
Yeah, data science actually is data enhanced based on the data analysis. So it's a little bit different, but we still are dealing with the data. So for example, scientific computing, we are dealing with the simulation data. Those we're probably dealing with the experimental data, but the data is huge, and we really need special techniques to handle that. So I think that they are closely associated. So by the way, who is teaching the computational statistics in your department?
Lei Ming. I think Lei Ming Chu.
I think that is a very important course. Yeah. If you want to be a very good data science.
Is that included here in the list?
I think in my slide I
It's the PhD in computing, I think.
Yes.
Okay, so we don't include it. We don't include 361 or 461?
It's 5.
Oh, so 5.
I mean, like expertise in computational science is super valuable because it overlaps with data science, which right now is the current super hot buzzword. And it's like data science today is like big data was like 3 years ago. Everyone says they're doing it. It's kind of like sex in high school. Everyone says that they're doing it, but nobody knows what it is. If you have the fundamentals for being comfortable with big data or data science, that gives you the skills to actually show up at a job interview and know what you're talking about, rather than saying, I'm a big data scientist and trying to rely on nobody knowing what that is to get you in.
Okay, I think it's about 1 o'clock, so I think we'll wrap it up now. And of course, I think we can stick around for a couple more minutes. If people want to have individual questions, we'd be more than happy to answer them. So thank you again for coming.
And folks, help yourself to cookies.